All right, recording is rolling. It is Wednesday, November 15th. We're on the schedule, this Wednesday schedule. We got slightly shortened class. Everybody look up here. Everybody look up here. So, you guys remember uh, the in-class quiz is going to be on Friday on energy and momentum. So we're going to do the review for that today. Uh, I do have your next FRQ printed up, ready to go, but I think I actually want to save that for tomorrow when we have a little bit longer class period. Right? And try this out earlier. So the review will fit in. And then about the last 10 minutes of class, coefficient of restitution lab. You guys remember that's the physics term for how bouncy is a collision. So you guys got some balls on your desk. You see some tennis balls, racket balls, bounce balls out there. Okay. How bouncy maybe against the tile floor. So I'll say that for the last few minutes of class. The interim period actually ends today. Check focus for this class, for all your other classes. Make sure all your assignments are in. I'm taking stuff all the way till Friday. So before the break, before Thanksgiving rolls around, make sure that you turned in everything for this class, including this momentum half page that we did together. I'm treating this as an extra homework assignment. A lot of you guys have already turned that in. Your chapter 6 puzzles, we've gone over all those. Well, actually, we didn't explicitly cover the ballistic syndrome, but I do have a poster for that. I bet you guys can figure that one out. Okay. And then if you want to hold on to those things until Friday for studying, you can do that. But make sure you turn this in before you leave for the break. Okay. And then yesterday I gave you guys your momentum take-home quiz. That's not due until after Thanksgiving. If you want to turn early, you can turn early if you like. All right, so you guys get what we're doing? All right, so review. Let me go back about 3.5 weeks here to the beginning of energy. So 2 units we're looking at. By AP's book, this is Unit 4 and Unit 5, right? Unit 4, energy, Unit 5, momentum. They have some things in common. There are conservation equations for both of these units that we can set up and then use to solve things from there. Right? All right, so here's a list of variables and units that you'll see for like Unit 4 and Unit 5, right? So we got energy, you can measure in joules. Work is a transfer of energy. Energy can take these different forms. I got another poster for this too, right? There's also power measured in, what does capital W stand for as a unit? Watts. 1 watt is like 1 joule per second. Right? So it's like a rate of work, rate of energy, right? Joules per second. Right? And then past couple weeks we've been doing momentum and collisions. Right? You can measure momentum, that's mass times velocity, right? Kilogram meter per second. And impulse is a transfer of momentum, right? That oftentimes quantified in Newton seconds. Guys, these 2 units right here, kilogram meter per second and Newton's time seconds, is that the same thing? Yeah, that's identical, right? Right. So you could use either or to describe either of those, right? So big picture units. When we started energy section, I said, okay, 1 joule that breaks down to 1 Newton per meter, right? Kind of like force times distance, right? Which breaks down to this in terms of the fundamental base inside units, right? And then one more step, a rate of energy, a rate of work, right? It's like 1 watt, which is 1 joule per second, which breaks down like this. So you can compare those two. You got that. Work is force times distance. That's a transfer of energy. Okay. Now this is a dot product, so you only multiply the parallel components. It got force and distance at different directions. Right? You only multiply in the same direction. So if you lift something for some height, right, you're applying an upward force and you're lifting it up. You just straight up multiply this, right? But if they're at different angles, you got to multiply by the cosine of the angle between them. Kind of like if you lift something up the stairs, the carrying up part, well, you have to lift up. So the up part you care about. That's like I see, cosine component, right? So cosine of that, right? Versus carrying something across the room. Like if I lift up an object and I carry it across the room, I'm not actually doing any work on it because the direction of the force is up and the direction of the motion is horizontal, right? Those have nothing to do with each other. They're perfect, right? So there's no work being done. Right? If you push a shopping cart, say down and forward, well, the shopping cart only moves forward. So only if the 4 components actually get multiplied together. Okay? Now be careful with something like this, because every once in a while the angle that you're given between these 2 vectors is actually like this angle down here. In which case it's not a cosine anymore; it becomes sine. Or what if you were given like this angle right here? Same story. It would be not cosine but sine. So careful about that. Right? Is it truly the angle between them? In which case it would be a cosine. Right? Now it's a little complicated. This is one of those posters you have to kind of stare at for a couple of minutes and anyway, right? But really, fundamentally, what it comes down to is this: work is force times distance. Boom. Right? Same direction, blah, blah, blah. Right? This graph right here, force versus distance, you will see this graph several times on the AP exam, right? Several versions of this graph here. You're going to see force versus distance. Every time you see force versus distance, I'm going to guess that the question is something to do with how much work was done, how much energy was transferred. Right. Now, in this case, I'm showing a constant force, but that doesn't have to be the case, right? You guys seen like variable force, right? If you're like increasing the force, for example, if you're stretching a spring, it takes more and more force to stretch it more and more and more and more. Right? That would look more like this. But the work done stretching it in the case of the spring, therefore the potential energy stored in the spring is the area under the curve. So, yeah. Right. All right, well, I've got new variables up here. Let's take a quick look at power. Power is a rate of energy transfer, so that's like work per time. Right. Now you can break that down like this. See, work is force times distance, so power could be force times distance divided by time. Okay. And you can group these two variables together and call it force times velocity. And a classic question for that could be like, if you're lifting an elevator, okay, so it's some weight you have to pull, tension, force in the cable is maybe equivalent force, right? And so you're pulling up at some speed, right? There's a motor at the top of the shaft, like drawing electricity off the grid, like some number of watts, right? How many watts? Oh, well, force times velocity. Now, if it's constant velocity, you can just very simply multiply together. If it's accelerating, then this might be true for one instant. It might be a little trickier because if it's accelerating, also that would mean that the tension force does not necessarily match the weight. I think you guys have seen stuff like that. Right? Now, this one you have to memorize if you want to use it. There's a pretty good chance that you might get one or two questions in the AP exam that this could be pretty helpful, right? So can you guys just memorize that, or be able to derive it, right? So boom, boom, couple steps, right? All right. Let's look at forms of mechanical energy. So back to energy, energy work. All right. So work is a transfer of energy, force dot distance. If you lift something for some height, see the force I have to lift it is its weight, that's mg. The distance I'd be lifting it would be a height change. Oh, mgh, that's that. Hey. So the work I do lifting it is equivalent to the potential energy that I end up giving it. Right? Energy transfer, right? Here's a more universal form of potential energy. I don't think I've ever seen AP ask exactly a question about that. So we're going to come back to that, right? Mostly focus on the gold rows. You guys mostly care about the gold rows. Come back to the green ones later. Mention this one later. Okay. Energy stored in a spring, 1/2 kx squared. I've seen many students over the years mix this up with Hooke's law, F equals kx. So there's a few formulas that are attached to springs. Next semester, we'll get into like oscillating motion with time period and stuff, right? But at this point in the year, there are two formulas you guys care about with springs. You care about the force is equal to kx, where k is the spring stiffness, right? Spring constant. X is how much you stretch it in this case. And the energy that ends up being stored is 1/2 kx squared. Those are two different concepts, right? Two different questions. F equals kx, energy is 1/2 kx squared. Okay? And finally, energy of motion, kinetic energy, 1/2 mv squared. And then when you guys come back from Thanksgiving in December, we'll get to rotational mechanics. And then there's a very similar like one that involves like wheels rolling down an incline, 1/2 I omega squared. Okay. But for now, again, like mostly focus on the gold boxes. That's not too bad, right? It's like 1, 2, 3, 4 gold boxes. Okay? Right. And with that, you can set up conservation equations. So if there's a closed system, that means no energy is entering or exiting the system. That pairs with there's no external force on or by the system. Right? So you can set up conservation, then you can solve for stuff. You say if it's a closed system, if you identify a closed system, that the energy you can't create or destroy. Now, if you have an open system, there could be an external force, right? Force times distance doing work on the object. So plus or minus, right? My classic example with this is a car braking to a stop. It starts off with some kinetic energy, 1/2 mv squared, right? And then force times distance, friction force times distance, right? Maybe it goes to like zero energy at the end, right? Mechanical energy, right? And so here's a really fundamental one. Galileo drops the ball off the tower. Maybe how fast is the ball crash landing on the ground? Right? This one you guys gotta know, right? You gotta know this one. Right? It's like so fundamental, and it's like a couple steps, right? So energy is conserved. At the top, it's all potential energy, mgh. Right before it's the ground, it's all 1/2 mv squared. You can equate those two. The mass of the ball cancels out. That was what Galileo was actually showing back in the day, right? The mass doesn't matter, right? And ooh, look, the crash speed is square root 2gh. You see that all over the place in physics. So you guys can really know that one, right? You guys know that, right? That would be a completely fair question for AP to ask you. It'd actually be kind of on the simple side for them to ask like an FRQ, right? How fast the ball crash landing, right? That might be a good quiz question on Friday, I think. Ooh, you guys haven't seen this one yet because I just made this new poster. But actually, you could have solved that with kinematic motion too, right? So I got a slightly different question here. What's the maximum height from a thrown ball? This is kind of the same question, just in reverse, right? If you throw a ball up at some speed, how high does it go? Right, goes hand in hand, right? You could have used this third kinematic equation from back in the day, right? Or here's the conservation of energy framework. Right? So they look a little bit different from each other, like going down both. But look at that; they lead to the exact same outcome. Right? So two different paths through the forest of physics lead to the same answer because physics is all self-consistent. You could also turn this around and say, oh, maybe you break out a matrix and say, oh, I know how high I can throw a ball. Hey, I wonder how fast I threw it to get it there in the first place. And just take this box, rearrange it, and get the throwing speed. Oh, look at that! It's square root 2gh. Hey, just like the Galileo question, right? Of course it would be, right? Oh, ooh, this one really encapsulates conservation of energy really well, right? Because it involves three different types of energy. Right? We got energy stored in the spring. We're gonna press this mouse against the spring. There's a spring constant. There's how much we smash it. Let it go. Pew, flies around. Now, as long as there's no friction loss, right? I'm treating this as a closed system, block, spring, earth system. Right? Of course, I'm focused on the blocks. So the blocks got to be in there. The spring, at some point, the energy was in the spring. So there's 1/2 kx squared, some number of joules of energy. It was like 100 joules of energy. So, ready to go. And then, see, by the time it gets to point B, like point A to point B, let's see, some energy went to lifting it. Oh, there's your gravitational potential energy. And whatever was left over, it's now in its motion. Oh, there's your 1/2 mv squared, right? Joules, joules, joules. These could all represent some number of joules. You can only add joules to joules, right? I don't see anything about force. I don't see kx. I don't see mv. Right? So it's all energy, like I said. Weird. Now, this one's a little more complicated, but I think you guys should be able to know this one too. Like, what's the maximum speed of the pendulum at the bottom? And so you can set up conservation of energy. Say, okay, well, it's all mgh at the top. It's all 1/2 mv squared at the bottom. This actually is kind of like the same as the Galileo question. Because look, the speed at the bottom ends up being the square root of 2gh, just like it was for Galileo. But the h now, okay, well, now there's some extra geometry steps, right? Can you figure out h if I tell you L and theta? I think you guys should be able to figure that out. All right, let's step through that. I see a nice right triangle right here. This leg of this right triangle is L cosine theta, right? Theta is the starting angle, right? And then L is equal to L, so that's the same L. So this height change between these two dashed lines is L minus L cosine theta. And if you like, you can factor out an L, and there you go. There's your H right there. L1 minus cosine theta. You guys see that? Okay. One more thing, I have in light gray ink here. What if you don't drop the ball or release it from rest, right? What if you give it a push, right? Well, then from an energy context, it has some 1/2 mv squared starting out with, right? Now, how does that work out by the, because I skipped some algebra steps from here to here, right? But how's that finish up? Now, notice what it is not. It is not final velocity equals initial velocity plus square root, blah, blah, blah. No. It's final velocity equals a giant square root of initial velocity squared plus 2gh, right? Guess it, right? That's how it, you can go through the algebra, but it's always going to work out like that. Same thing here. I got a question earlier. Is that the same thing if Galileo throws the ball? Let me go back a few posters. Right. What if Galileo throws the ball down? Right. Let's see if you guys are following. Would the crash speed be his throwing speed plus square root 2gh? Or would the crash speed be square root of throw speed squared plus 2gh? How about the second thing I said, right? Yeah. That's consistent with that right there. Right. Oh, I had you guys do this lab. So you guys did the calculation, what ideally should the speed be at the bottom. And then you guys had that speed gate and tested it out. So you guys did a comparison. And a lot of you guys' labs, it was like, oh, it's pretty close to the same all the way down. Right. Ooh, roller coaster minimum height to get around this curve right here. Right. This is a really classic question. Now, this one's has some complexity to it. This is probably a little bit outside the scope of maybe what AP would ask, especially on multiple choice. All the multiple choice you should be able to answer in 2 minutes. Okay? But I bet a lot of you guys are going to take physics in college as part of maybe some science track. And this is a really classic question, so there's a really good chance you'll see this in the future. Here's how I solve it, right? Now, so point A to point B. All these energy equations, look, they're always from like some point A to some point B. Say no frictional loss, right? Conservation of energy. Right? Now, I know at point B, there has to be some speed. It can't be zero speed or it's going to fall off the track. And that goes back to the section before this with like centripetal force, circular motion, right? That's what happened in this green box right here. So I'm telling you what the minimum speed has to be, or at least what the square root is. Right? I'm going to take that. Right? The minimum speed is square root GR. Right? And here's how you get it. Right? Now, conservation of energy. Well, if it's all potential energy here, LMGH, and I'm measuring H with respect to this ground level way down here, that means by the time it gets to like point B, that it does have some height. So there's some potential energy. So MGH turns to MG, and then, 2R. Hey, that would be the new height, wouldn't it? 2R, right? And whatever's left over goes into kinetic energy, 1/2 mv squared, right? And it better have some speed. How much speed? Oh, well, we answered that already with all the centripetal force. Right? So then you work through the algebra, blah, blah, blah. This is always the answer to that question, right? This is like the theoretical minimum height. stay short of that, but no way does it ever get around. Car brakes to a stop. This is the classic open system that I was talking about before. Right? I did go back and amend this poster a little bit. I offset this distance so it doesn't look like a force vector. It's not a force vector, right? The distance isn't right. This car braking to stop has 3 vectors on it. Its weight, the normal force, and the friction force. Okay? Right, so from an energy point of view, it looks like this. Let's say there's an open car, and I'm only considering the car is in the system. Right? So a system consisting of only the car. Right? The car starts off with a bunch of 1/2 mv squared. Right? And then, so there's some number of joules of energy. And then that friction force acts for this distance, right? Force times distance. And notice that they're opposite direction. So that's why I subtract, right? So it's like cosine of 180 degrees. It's like -1. And the car will have 0 mechanical energy at the end. There's no hills here, so that's right. And then now here's where you're gonna make a few substitutions. See if you guys remember this. What is friction force compared to normal force? There's an equation that links those two. Normal force times coefficient of friction. Yeah, friction force is coefficient of friction times normal force. And the normal force for this pretty straightforward setup, just a level road, right? Is that going to be equivalent to the weight? Yeah, right. You could say, well, the spin of the Earth are different by like 0.3%, but we always just ignore that, right? Yeah, so put it all together. This friction force is coefficient of friction times, and then instead of the normal force, we'll say mg. Okay, and that distance is that distance. You can solve for distance. The mass of the car cancels out. I've made that point a few times. It doesn't matter how massive the car. If I say you have a light car versus a heavy car, all else equal, they'll also have the same braking distance because look, mass doesn't show up. Right? And the distance is also proportional to the square of the initial speed. So if you like triple the initial speed, you get 9 times the braking distance. You guys remember that too? Right? Use that too. So here you go. There's an open system consisting of only the car. Okay. You could use conservation of energy to solve outwards. Like the classic question with this process would be like, how fast is one of these blocks moving after falling for some distance? Right? Notice with all these conservation of energy questions, I haven't mentioned anything about time. Like so many seconds have ticked off. No, right? None of these, right? But it maybe mention like how far something's gone, right? Conservation of energy. So if you ever see the question like after it's fallen for like so many meters, how fast is it going? Probably the fastest way to solve that is with conservation of energy. Right, so the fact that the large block can fall is like supplying all the energy with potential energy, gravitational potential. Right? And that's going to go into, in this case, 3 places. It's got to lift the small block. So there's your mg of lifting the small block. And then whatever's left over goes into the speeds. Right? So kinetic energy, 1/2 mv squared, 1/2 mv squared. And they're the same speed. So you can factor that out if you like. Right? Solid. So conservation of energy. Right? That's not the only way to solve this. You could alternatively calculate the acceleration by saying, okay, well, if I know the masses, I could calculate the acceleration. Then so that's dynamics, that's unit 2. You go all the way back to unit 1 with those 3 kinematic formulas to say, see if it's fallen some distance, picked up some speed, right? So you could do it that way too. It's probably a little bit longer process to get the same answer, right? And if you're ever told like it's fallen for some amount of time, actually probably would do it that other way, right? But if it's fallen some distance, this might be the fast way to do it. Here's like a modified Atwood, just a little bit more complex. Right? Let's say there's like a drag force here. Say, well, okay, the large block falling is supplying the energy. You treat this open system to subtract the force times distance of the drag force, and then very similar. Right. Simple machines. Here's ways you can get a mechanical advantage, which means that you can amplify your strength. That doesn't mean you amplify any energy. Conservation of energy still applies, but you can become stronger. Right? You guys set up some pulley systems. So you could lift something that very heavy with a small input force. The catch was you had to pull lots and lots and lots of string to lift it just a little bit at a time. Right. And then here's a bunch of other ways to get mechanical advantages. Oh, here's what you guys did. So here I'm showing mechanical advantage of 3 to 1, 3 to 1. So like 3 times as strong. Where are you? There's a difference between 2 kinds of mechanical advantage. Right? There's the ideal, which is based on geometry. Right? But there's actual. What it actually is the output force compared to the input force. Right? Maybe it's a tiny bit less. Maybe it's like 2.751. And you guys tested it out because here's the lab that you guys did. You guys rigged up different pulley systems, tried it out. Right. We could have done this one. We didn't quite do this one, but if you get leverage, right, with a lever, right, suppose you got a shovel trying to lift a boulder or something, right? Like that. Similar type mechanical advantage. There's mechanical advantage. Suppose there's a box that's way too heavy to lift. Somehow be able to slip some wheels under it and push it up at the incline. Get mechanical advantage. There's mechanical advantage like a like a wheel system, right? Which is actually just like a lever system, just turned into a circle, right? Same things like getting leverage, right? But yeah, same story. You pull lots and lots of string here, and this only moves up a little bit at a time. Uh, oh, this poster is new. I did give you guys these notes. This is in your notebook from a couple weeks back, and I went home and said, "Oh yeah, this would be a good poster," so I went and make this. Right. So here's the universal form of gravitational potential energy. And the one place I remember we did kind of use this was to solve for escape speed. If you're sending a rocket like to Mars, escape speed, right? The catch is that this gravity field is not constant, right? But if it is approximately constant, you can just use MGH, right? So what's the connection from here to here, right? And then in your notes, I showed you guys this whole process where you can prove this from this, right? So you go from top of Mount Everest down to the sea level. That G doesn't really significantly change. Okay? It's about 9.8 per second squared. All right, so that is all the energy posters. Okay. I'll switch over to momentum. Momentum. So momentum is mass times velocity. We're back to the vector value. Like all that energy we just did were all scalars, right? But now we're back to vectors. Right? So directions are really important. Momentum is conserved in closed systems and applied to collision physics. Whenever you see a collision physics, start thinking something to do with this, right? With the exception of if something collides with the spring, right? That you normally just ignore this, right? But if it's like two blocks colliding, say, okay, something to do with this. And momentum is conserved in closed systems. So if they're like two objects boing off each other, right? If you have all the mass times velocity bits before the collision, it equates to all the mass times velocity bits after the collision, right? Now remember, if you got opposite directions going on, somebody has to be positive and somebody has to be negative because vector values, right? But then, well, what kind of collision could this be? Like, what if these objects stick together or bounce off each other perfectly or have to play tennis balls, right? Regardless of how bouncy these objects are, this expression down here is always, always, always true, right? Whether it's clay balls or tennis balls or marbles, right? This is always true, right? So let's dig a bit more into like extreme kind of collisions. At one extreme, one boundary conditions, that objects could stick together. That's called perfectly inelastic and very similar to formula. Actually, it's a little bit simpler because you just make one giant mass, some kind of velocity. Right? So it's like two balls of clay. The other extreme, on the complete other opposite end of the spectrum, is something that's completely bouncy, which is pretty close to that right there. It's probably about as close as I could show you. Right. And the physics conditions are, well, not only is momentum conserved, which is true for all collisions, but also kinetic energy. And here's the result system equations from that. I will not expect you to memorize that. So you don't have to memorize that for Friday. And AP is not going to ask you to memorize that either. But there it is. That's how that works out. You might see that in college, in which case pull out your notes from high school. That's the answer. Here, this one's new. You guys haven't seen this one yet. Just made this one new. Right. So I put this on a convenient table. Here I got a spectrum of different kind of collisions. Right. So general collision. Here's perfectly bouncy. Here's perfectly sticky. Right. And then for funsies, I throw on an explosion at the end, which could be like a grenade exploding apart. I think through you guys' question like that. Well, we never actually saw that Matrix School Bus question. You guys remember all those kids were on the frictionless field? And like if you throw a baseball one way, you get kicked back the other way, right? You could actually do conservation of momentum to solve that. Possibly tomorrow, if we have some couple spare minutes, might do that, right? But for every single one of these scenarios, momentum is conserved, right? And you can use that to solve stuff, right? But what happens to kinetic energy? Keep your eye on that. Well, perfectly bouncy, it's also conserved, but that's the only one that's going to be the case, right? In general, it's going to decrease kinetic energy will. If it does stay the same, then we're just back to perfectly bouncy again, right? Perfectly inelastic, the kinetic energy always goes down. And if you have to explain why, be ready to pull out a phrase like permanent deformation. AP graders might like that one. They might check off that box, right? Two balls of clay, but there's some force times distance that one did deforming those objects. Right? And then if it's an explosion, like a grenade explosion, well, that case the mechanical energy will increase. Or if a pitcher throws a ball, ooh, I bet you got some energy that came from muscles, right, to throw the ball. Okay. Right. You guys did lab version of that. Got some lab tables, right? Now, what if you want to quantify where on the spectrum are you, like how bouncy is something? This is what you guys are going to do later today, coefficient of restitution. So that's defined as what's the post-collision difference in velocity compared to the pre-collision difference in velocity, right? So, okay, careful, you got differences of positive, negative. If you minus a negative, same thing as plus a positive, careful with that, right? And a specific version of that is bouncing a ball off the floor, right? Where the two objects colliding are the ball versus the earth, right? Now, it's a material property, so maybe a tile floor versus a carpet floor would play out differently, right? So I'm looking at what is the rebound speed compared to the crash speed. Here's your rebound speed, here's your crash speed, right? That's coefficient of restitution. Now, how do you get those speeds? Oh, I know how I'm going to get those speeds. I'm going to go all the way back to 1589, Galileo. Hey, look at that. There could be the crash speed based on the drop height, but also the rebound speed based on the rebound height. Couldn't that be? Right? Right. So here, that's those two expressions. You substitute. The 2G cancels out. You get this. The 2G canceling out. That means you could take this whole system to Mars, and I bet you get the exact same outcome. You know, if you brought the whole tile floor with you, right? Because it doesn't matter how much gravity, just as long as there is gravity. So you guys do this later. You guys measure with the meter stick. What's the drop height? What's the rebound height? Take the ratio, and then take the square root of that. That will tell you coefficient of restitution, how bouncy is the ball off the tile floor. Right. I'm gonna have you guys copy this table here in a minute, but hold on. Come back to that one. Right. Closed system, open system. So a little bit different perspective. Closed system, momentum's conserved. Right. If there is an open system, delta P. What's the fancy physics word for that? Starts with an I. Impulse. Aha. Hey, there's impulse, which is force times time, which is kind of like, remember, work was force times distance, energy transfer was force times distance, momentum transfer, impulse, is force times time, right? Now, if you have a constant force for some time, it could be like a rectangle, right? Really commonly, you'll see graphs that are like triangle type shape, and you're gonna see several of these graphs on the AP exam, right? Several of these graphs, you're gonna see force versus time. Whenever you see force versus time, start thinking, okay, something to do with momentum transfer, something to do with impulse, right? And that'd be, it's going to translate to mass and change the velocity of the object in question, right? So maybe this could be like a ball, like open system, external force, bam. Right? Ooh, here's a new poster. Well, I think we covered this concept. I just made a new poster. Right? What if you have equal mass, equal velocity, except one sticks inelastic and the other boing bounces close to elastic? Right? Which one sends the bowling ball moving faster? Elastic. Right? So the change in momentum would be greater than the original case. Right? Ballistic pendulum. So this is the one in your homework we never quite got to in class, but I think you guys can figure out. Right? So here's this. The question is usually, what was the firing speed of the bullet? So forward in time, there's a collision, and then it swings up to some height. And maybe you can like measure the height change. Right? So you saw this backward in time, saw its conservation of energy. Say, well, if it went to some height, then how fast did it going post collision to get up there in the first place? And then you step backward in time and say, well, what collision led to that post collision speed? Right? And then the momentum all came from bullet, blah, 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 stuff like that. Right? Now, there might be one extra step in here that I did not cram into this poster, which is you can actually calculate that H, that height difference, based on L and theta. So you might have to do that too. Look for something like that. Right? And collision in 2-dimension. So if you ever see something like this, like billiards or shuffleboards, all right, you got momentum is conserved along each axis. Right? So you can solve something like that. Right. I think that's all the questions we got. All right, so there you go. There's the review for Friday, and then tomorrow we're gonna mostly do that FRQ. Got some prepared, and maybe some other things. You guys got a half page on your desk? Half page. All right, write your name on your half page. Everybody, write your name. Write your name. Copy down that table. So we're gonna try different trials. So pick a ball that you like. There's lots of different kind of balls out there. Okay. And measure what is drop height. Try different drop heights and see what's the rebound height, and then calculate the coefficient of restitution, which I just showed you guys how to do. Right? Take the ratio of height, take the square root. Right? And also draw a graph. Draw a graph of this thing. So I had a graph ready to go. Try this thing. Okay. All right. So yeah, try different drop heights, different rebound heights. Hey, I wonder if the coefficient of restitution is going to be the same regardless of the drop height. You can figure that out. Right? And then notice this note down here at the bottom, graph rebound height versus drop height. I wonder what this graph is going to look like. Here, I set it up for you guys. Rebound height versus drop height. And then, I labeled and scaled the axes. You guys do the same thing. Maybe you can put this graph on the back of the same paper. So on the front, you have the table. On the back, you have the graph. Right? So just choose the same ball over and over. Right? Say, how bouncy is the ball? And then one like this. Guys, here, let's do a quick trial run. What's the coefficient? What's the coefficient of restitution of that right there? 0, right? Because there's 0 rebound height. Right? 0. Oh, okay, yeah, that's inelastic. That'd be 0, right? Versus the bouncy ball. Ooh, I feel like I've seen numbers earlier today of like 0.8, 0.9.
That does be really dumb.
All right. So with that, I'm gonna shut off this recording. Just turn in this lab to the grade tray by the end of class today, and yeah, and we'll do FRQ tomorrow.